Okay, so yesterday I introduced a few concepts about the energy functions that are used for simulations, the different kind of models, and today I'm going to talk about probably the more finer grain type of models that can be done other than the quantum. So I'm going to be talking about large-scale simulations of molecular biophysics. So I'm going to talk about three kind of systems, and I'm telling the story like a Old West story. So this is a Clint Eastwood movie from the 70s, actually called The Good, the Bad, and the Ugly. And you may remember because it has a whistle that that's the good, the bad, and the ugly. So I'm going to tell you a story about the good, the bad, and the ugly, and I will whistle every time if the chair falls asleep. So the good, in my opinion, is protein folding, protein dynamics. The bad is nucleic acids. Pretty damn difficult to do nucleic acids. And the ugly is membrane proteins, because membrane proteins are difficult and are ugly. I mean, when you look at the complexity of the problem, and then each one of them has different problems that have to be solved, and then for different problems, different techniques and different tricks can be used. And I will introduce some of the tricks. Those of you who are more inclined into the statistical mechanics and so on, maybe will enjoy a little bit some of the flavor. I'm not going to go into the details, but of the flavors of the tricks that are used, which are similar to perturbation theory or actually thermodynamic integration. So here goes, the good, the bad, and the ugly. So that's already, I mentioned that. And so these are the plans for the talk. I'll introduce a little bit enhanced sampling methods. Mostly I will talk about replica exchange, and I will talk about replica exchange. It's also called parallel tempering. Depends on which field you come from, and just introduce on how this can be used to solve or enhance a little bit the sampling, so that you can actually look at processes that should take very long time scales, and you can actually resolve in simulations that are of much shorter time scales, and still preserve the thermodynamics. So you get the proper sampling or the proper weights for the configuration, so the thermodynamics is correct. The dynamics is all messed up. Tomorrow or whenever is my next lecture, I'll show something that has the kinetics on it when you want to actually look at the time resolved processes and how you actually can also simulate processes and infer timescales that are order of magnitudes longer than your simulations, given approximations, of course. So here are the different systems we work with, and so essentially there are these models in here. This is what I introduced yesterday. You take these models, you simulate biomolecular systems. Here are some examples. These are reverse micelles. We actually have studied self-assembly of reverse micelles with proteins inside. This is a GPCR protein with a G protein bound to it. This is just a lipid bilayer. This is micelles, reverse micelles coalescing. Actually, in the whole self-assembly, you see a lot of processes. And these are pore formation in lipid bilayers. These are slow processes, actually, each one of them. And this is the ugly. It looks ugly. I mean, that's... and then in terms of theory, there are many aspects in here. I'm only showing here a sketch for parallel tempering, but there is a replica dynamics. That is a way of enhancing time sampling rather than thermodynamic sampling. There is Markov models, there is string methods, so many things can actually go here. I will touch briefly on some of them on the lecture tomorrow, not today. So today, time resolved is not there. And then you put that into computers, you crank, and then you have to compare what was measured with what you get, and what do you learn, and then in many instances you actually work or interact with people who are doing the experiments and suggest experiments, 10% of the time they're willing to do them, which is a lot. That's not bad at all. I consider it success when somebody will do the experiment and try to verify or essentially test the prediction that we have made. And if we get the prediction right, even better. But if we don't get it right, we suggest an experiment, and then we learn something out of it, and then we go back to the drawing board. So here are the problems that you face when you do biomolecular simulations. So these are 4 typical systems that fold in time scales of 1 microsecond, or could be 10 microseconds, or faster. So these are the 4 systems in here, and they all have been studied experimentally, so that's why they're very good test systems. And essentially, we study the folding and unfolding of these systems from scratch. No, just a force field, no other fittings, nothing else. And then we compare to experimental structures in many instances. For some of these, we actually compare helix coil transitions and thermodynamics, and we actually test some of the methods that are used for interpreting experimental data, and we can do more sophisticated fittings because we actually have details in the simulations that the experimental data doesn't have, and we test some of the approximations that are made. So let me tell you what are the caveats about these systems. So this is a completely disordered system. So this is a sequence very much is GQ, 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 makes nothing. It's just a loop. So this system was studied by Bill Eaton and Lapidus. And the trick here is that you put a cysteine in here, and you put a tryptophan in here. The cysteine will quench the tryptophan. So the tryptophan is fluorescent. When the cysteine donates an electron, quenches it, fluorescence stops. So you can actually time resolve and measure when the system is open, it fluoresces. When the system is closed, it's quenched. So you can actually measure the time it takes for the system to open and close. And this is done in a microscope, so you can actually look at a single molecule level what's happening here. So here is the good thing about time scale. So if you measure what is the time scale, how long it takes for this first amino acid to touch this last amino acid. This is 11 amino acids total, just opening and closing. So this is completely disordered, no secondary structure. How fast does it occur? It's 10 nanoseconds. So if you consider this is the fastest time scale that you can consider in the sampling of a chain. So you have a chain that is disordered, is configurationally diffusing around, and just 10 amino acids to find each other. It takes 10 nanoseconds. So what is 10 nanoseconds? If I were going to do the calculations on this laptop, it's 10 days. I can get about a nanosecond a day on this computer. And workstations in the 2005, that's what you got. Nowadays, you buy a GPU, 8 GPU machine, we get a microsecond a day. Yeah, that's on systems bigger than that, actually, systems bigger than that. So that's a time scale that is easy, right? 10 days, one computer, easy. So ask your grad students, are you willing to do it? They should all be willing to do it because it's a good test and it can be done. Now, an alpha helix formation. So here you start from a random coil from something that is completely disordered, more or less like this, and then you look at the formation of an alpha helix. So you're going to get this type of secondary structure. And you do the calculations, it actually takes 200 nanoseconds. So now from 10 days is 200 days. Still willing to do it? Yeah, it's very much part of a year. The trick is that you don't do it in one computer. You try to get 200 computers and do it in one day. And that's where parallelization and all kind of tricks can come up. It doesn't work, but you get it in 2 days if you have the 100 computers. And here you have a much more local structure. So you have this II+4 type of hydrogen bond. If you look at the Simbrack type model for helix coil transition, it's a very cooperative transition that once you nucleate the helix, it keeps growing and it can nucleate anywhere along the chain. And once you have grown a nuclei, which is about a turn, it zips from there and it makes the alpha helix. It's a very fast process. So that's a system of about 20 amino acids. Is there explicit solvent? Yes, yes. So typically, these were done tip 3P. It's the cheapest water model. That's why when he suggested yesterday a good solvent model, no, a solvent model. Yeah, it's good enough that it has dipoles and it competes between interacting with the protein, and it competes between making a structure. It doesn't make quite the right structure. It doesn't have quite the right dynamics, but it has the competition between them, and it's cheap. So, we have done this calculation, tip 4P, tip 4P equal, never did tip 5P or anything like that, but we have tried different water models, and actually, the more sophisticated water model you put, the worse the result you get in this life. And then, so here is another system. This is a beta herping. Notice the time scale from 10 nanoseconds to 200 nanoseconds. Now we're in the microseconds, so almost a factor of 10. So factor of 10, it's the same. And this is a beta herping. What is the problem with the beta herping is that there is no easy, when we compare to the alpha helix, the alpha helix can nucleate anywhere. Essentially, you make the II+4 hydrogen bond, and it zips from there, and it's a very cooperative type transition. It just zips through, and kinetically it's very fast. When you look at this, a beta herping can essentially close in many different places, and only one of them is right. So it's trying this time scale over here of different segments finding each other. So it forms and breaks, forms and breaks, forms and breaks. And there are two mechanisms by which a herping can form, and these have been studied. This has been studied by, this was studied by Eaton and Lapidus. This was studied by Eaton and also by Dyer and Woodruff. This was studied by Victor Munoz, who's going to be here. I'm glad I'm talking before he came, because he's going to disagree with everything I say. But we agree, I mean, he measured it. So there are two ways of forming the herping. One way is that you can nucleate the turn in here, and then you zip through. Another way is that you make the end-to-end contact at the right facing, because if you make the wrong facing, there is no way that you can slide through and form it. You have to break and form again. So that's why this process is much slower. So people will call that internal friction. They will call it the configurational entropy. This is more of a funnel-like. This is not a funnel-like. You can use any language you want to do that. So this we actually can simulate too. It takes longer. And here comes what I consider the simplest protein, the simplest fold. It's a 3-helix bundle. Just 3 helices, 3 alpha helices. This is a protein called protein A. All this is explicit solvent. And interestingly, folding of this protein that has 59 amino acids is as difficult or takes the same amount of time as folding a beta herping that has 16. So that's the difference between beta sheets, beta herpings, and alpha helices, that the cooperativity actually speeds up the process. So I'll show you, I'm not going to show you any of these systems. We actually have studied these. There's some papers, 2001, 2002, Garcia and Botmatsu, the same for this one. This was with Jose, 2003. And look at this. And that's when life gets really difficult. This here is this protein. So this is just at scale. So if I look at this protein, that's this protein in here, and this is the ribosome. So this has 20-some proteins. It has thousands of nucleic acids, bases. This is a whole machinery that actually synthesizes proteins. And so forget about folding that. right? So if this takes microseconds, this is going to take, actually in the cells takes pretty long time to make this. The cell typically makes these ribosomes and they stay formed very much. People have studied the folding of the ribosome by looking at different segments. RNA is really difficult because RNA, there isn't such a thing as a funnel for folding. RNA, just 4 letters, is a very rough energy landscape. And essentially the sequence determines a lot of the folding. And in nucleic acids, you can have transitions from one form of RNA or DNA to another. In the lab, it takes days. You go from right-handed to left-handed. People will do a fiber, they change the conditions, they come the next day, and it has changed. So forget about modeling day processes on fibers. These are slow systems. So we're not doing that. Carissa Matsu actually works on that. Paul Whitford have worked on this using minimalist models, and this is fantastic work. I mean, when you look at they have looked at the whole process. So this should give you an idea what can be done. This is at the atomistic level. This will be at the minimalist model level. Carissa Matsu has done, at Los Alamos have done 10 microsecond simulations of this. It's 2 million, 3 million atoms. It's really, really big. You can always go more coarse grain, right? It's a sphere with a center of mass of a radius r. That's really coarse grain. And I mean, you can figure out what the diffusion coefficient is. Yeah? Yeah? Well, like always, Diego mentioned that yesterday. What's your question? That's your model, right? So it depends a lot. If I want to do this model at the atomistic level, and then I calculate diffusion coefficient, I wasted my time, right? Because the radius tells me that. If I do this model at the coarse grain, and I ask what's the catalytic rate, I just wasted my time, because actually didn't waste too much time, as if I would have tried to do the catalytic rate with the quantum chemistry. So it depends on the model. Whitford, if you look at the papers that they have, so they have looked at the tRNA coming in and positioning. Yeah, but haha, yeah. Peop- people people have looked at the assembly. I'm not very familiar with the literature, so there are 2 subunits, and there is some papers by Bustamante where they have taken some segments, a fragment, pretty large fragment, they pull it, and then they see how it forms and breaks and so on, and they have papers on how RNA folds based on those pooling calculations. So many pieces of it have been taken out. Now, the assembly of the whole complex, I mean, it may have been studied, but at a very coarse grain level, where probably they're looking at what's the size of the molecule under different conditions. I know that you can start deleting some of the proteins, and people have looked at what they believe are ancient copies of the ribosome. And it is believed that ancient copies of the ribosome do not have the proteins. They just have the RNA. And people have tried to build those. Then catalytic rates and whatever are, very slow, because it's a much fluffier system. So yeah, I'm not an expert on ribosomes, so don't ask too much. Ask Paul. He's gonna be here next week, right? Yeah. Very good. Yeah, yeah. Angel said that this was all full of great ideas. Yeah. Proteins is like a scaffold that it keeps things kind of close together. things, I mean, I don't want to go into all the details of the ribosome because I do not work on the ribosome. So I'm doing this more of a tutorial and showing the complexity of what a real machine may look like. And yes, it's a machine. Yeah, it's a screwdriver. Yeah, but things that you don't see here. I mean, this is a system that if you just take a nucleic acid, it has a charge of minus 2,000. Right? Every nucleic acid has a phosphate that has a -1 charge. Things are within almost touching distance, these charges. So you have magnesium everywhere. You have magnesium ions cross-linking different regions. And yeah, and if you don't have those, even the folding doesn't occur. You have to have, they're like, they play the role of disulfides in proteins, so they actually attach things. And the proteins play some of that, right? It just stabilizes the system. Yeah. But I haven't looked in details at all these experiments on ancient RNA ribosomes without proteins, for example. So these are the typical, for folding, people doing folding, S6 is one of these very popular proteins, is one of those. I don't know which one. Yeah. All right, enough ribosome. So what are the problems here? So the story I made it is you ask a student to do a calculation like this, takes 10 days, takes 200 days, takes 1,000 days, or 10,000 days. The student, you ask a student, you want to do a calculation, it's going to take 10,000 days on the computer. They say yes, you fire them. Because come on, you have to think. You cannot spend 4 years trying to finish a calculation, actually almost, 7 years, trying to finish a calculation, think, how can you do it in less time? Think for 3 years on how to do it in half a year. You gain something, yeah. At least you can do it twice, yeah. So these are the problems here. So how do you actually do that? This is one of the methods that has been very useful for biomolecular simulations. So almost many of the protein folding calculations at this level of detail are done with this parallel tempering method. And very much the trick is that you, it's a little bit of a counterintuitive trick. So you have a difficulty simulating one system, just to 100. Right? That's the logic behind. But the 100 or 50 that you're going to do, they're going to be at different temperatures, such that the sampling of the general landscape or of the multiple minima that you have in the system is more efficient. At high temperature, you're going to sample broadly, and then once you find minima, you can actually cool down the system or exchange with systems that are at lower temperature and then dump into those systems. You can, in a single step, change the temperature of a system. Imagine you have, actually this is an example I give here. Imagine you have a system at lower temperature, blue, and a system at higher temperature, red, and the system at the higher temperature has lower energy, is in a state of lower energy than the system at high temperature. You can exchange them, exchange the temperatures. So from now on, this system is going to be at the temperature of this one, and this system is going to be at the temperature of that one. And if you satisfy that condition, you will always accept that move, because the state that you go has higher weight higher Boltzmann weight than the initial state. However, if you do the opposite, you can still accept the move, and that's where you use a Metropolis Monte Carlo. But the Metropolis Monte Carlo is that you create an ensemble of systems. So you're going to have, say, 50 systems, and the 50 systems are non-interacting, but what you have is a Hamiltonian of 50 Hamiltonians, each one of them at a different temperature. It's a pseudo thermodynamic equilibrium. And then you do Metropolis Monte Carlo on that ensemble, and you choose one configuration, you exchange it for another configuration in the typical way you do Monte Carlo. But when you're exchanging temperature from one system to another, the formula that you actually get is this one. And it's easy to be derived. It's just Boltzmann sampling for exchanging this system to that system, and then the Boltzmann sampling for changing this system for that system, but at a different temperature. And the probability is the multiplication of the probabilities where the systems are not coupled. And then you get this transition probability. So this is the beauty of the transition probability. It depends on the difference in energy. So like I mentioned before, if the system at the highest temperature has lower energy than the system at the lower temperature, than the system at lower temperature, that exchange is always accepted with probability 1. So this function is going to be 1 for that case. And in the other case around, this function is whatever it is. Whatever is the difference in energy. But notice that you don't divide by the kT. You divide by the difference of 1 over kT. You multiply by the difference between 1 over kTs of the two states. So these energy differences can be huge because this temperature difference, these effective temperatures are huge also. So it depends on how close the two temperatures are because it's the difference in inverse temperatures. So I can define an effective temperature. People hate this analogy. And that effective temperature is the multiplication of the two temperatures divided by the difference between the two temperatures. And I put absolute values because 1 and 2 could be either one. So notice 300 degrees Kelvin versus 305 degrees Kelvin. For the matter of argument, this is 300 square. So that's 90,000 degrees Kelvin divided by 5. So that's 18,000 degrees Kelvin. So how much the energy difference can be is 18, it's going to be 18,000, so that's 300, that's 60 times kT. So this energy can be 60 times kT, and you can exchange those very easily. So that's part of why this method is quite efficient. And then if you satisfy this condition, you're doing Boltzmann sampling. So at each one of the temperatures, you're doing a canonical ensemble averaging of your system. It's equivalent to Monte Carlo, and the molecular dynamics part of it is that the configurations are developed by molecular dynamics at constant temperature. So you actually do temperature couplings to each one of the system. So it sounds beautiful, everything is great. Does it work? Damn, it does. It works. It's very efficient. So this is the algorithm on how you do it. So you just decide to exchange or not. I'm going to go into these details. You can actually follow the history of temperature of a system. It goes up and down. There is advantages. It's easy to parallelize because all you need to do between processors that are performing the calculation is tell me what's your energy, what's your temperature, 2 numbers. And then once I decide that, I can decide what the exchange is. So it's essentially uncoupled systems or very weakly, they call it embarrassingly parallel. I'm not embarrassed at all. It's very weakly coupled systems, actually almost not coupled at all. And let's go back to that after this. So here's protein A, 59 amino acids. We did it, this system has 6,583 water molecules. So it's a box, has to be large enough to hold the unfolded state. Purple is the folded state. Cyan is actually the structure that we get. And this was published 2003. And actually, we get a structure is 1.2 angstroms from the actual structure of the protein, and the force field was crap. Right? It's you get the right structure. In this case, this was with the Amber 94 force field, which likes alpha helices. That was on our advantage, but actually you get this the fold reasonably well. Notice that the side chains are also very well packed. And this is because replica exchange. So these calculations were about half microsecond per replica. There were 64 replica, so it's about 25 microseconds of computer time. In 2003, that was about 1,024 processors for 225 days. Yeah. So that's, and the stupid student who did this was me. Because you cannot ask anybody to do it because it's not clear it's going to work, right? This is, all the ingredients are there. Try a system, it's just computer time. See if it works. And, you know, you get something, it works, you know, when you look at the details, yeah, right. Caveats that we got from this system. So you see 3 helices. So this is helix 1, helix 2, helix 3. This helix packs on this side, it also packs on the other side. So you have the fold like this and the fold that it goes the other way around. Oh, I got grief for that. Guy Monteleone, who did the NMR structure, says this is full of, you know, not nice words. This is being recorded. We have done experiments, it's never there. So this is, how can you show that? We said, well, you do a calculation, you show what you got in the calculation. I'm not going to show just what agrees with you because then I'm deceiving, right? That's very typical in the field that people only show the part that agrees, they don't show you the part that doesn't agree. So you always think things are great, then when you do it, they're not. A few years later, actually, this was not published until 2012. The fact that we got these mirror images. And a couple years after this, but we had these results since 2009. This, and after this, actually, Sheraga published with his force field exactly the same. They get the inverse, and they believe it's real. Actually, there is a Villa in Argentina is working with people to actually measure. They believe it's, that there's these 2 possible packings. But the NMR is not easy to see, or it's not there. It's not clear what's the case. I skip. Yes, 64 in this case. Yeah. Kinetics or no. Well, I'm not saying what is the time scale at which it happens. I have an ensemble that has the 2 populations. So out of the 64 replicas, how I discovered this, right? So typically, what you do is that you folding, I consider it as a rare event, right? So you're doing your calculations, and then you have 64 copies, and you start your calculation, and within 10 nanoseconds, one of them folds. You jump off the chair and say, oh, wow, that's fantastic. And then you wait 30 days and another one folds. And you keep, and then you can make a plot how many have folded at this time and how many have not folded, and you can extrapolate how long it takes before they fold. And then I extrapolated and then keep simulating, and they don't fold. And then I look at trajectories, and you look at the trajectories and they fold. You look at quantitatively, RMSD or whatever, they're 7 angstroms away, so they're not folded. And say, is my RMSD code broken, right? Is it a bug or whatever? And then you try 1,000 different things. And it's, but by eye, you cannot tell this versus that. It's just 3 helices, they pack. So actually, there were like 6 or 7 replicas that folded into that, and they were very stable. They even came down to low temperatures and stayed there. So they populated the ensemble. So in terms of an ensemble, they were both populated. The right fold was there most of the time. The wrong fold was there 10% of the time. So no kinetics, but kinetically, these systems fold very fast, right? It's microseconds, so it can open and close into one or close into another. Experimentally, it is believed that it only folds in what I call the correct folding. So there are a couple things here. One is that probably the force field is not good enough to tell the hydrophobic surface that you form on this side versus the one that you form on this side, these contacts are, the energetics are not as different as they probably are experimentally. That's why you see it. So it's essentially, it's too rough. The energy might be too rough and not be able to distinguish those things. Another possibility is that it's there 10% of the time. 10% of the time on these experiments, it's very difficult. You cannot see things. If you have an NMR spectrum and 90% of the time is giving you one structure and 10% of the time is giving something almost identical in terms of close range, but far away, things that are far away, you might not be able to tell. So Guy Monteleone is going to see this and he's going to send me a knife through the internet, put it in my heart, because it's completely wrong. Yeah, the NMR structure is perfect. Yeah. So here is how computers have changed. So actually, the protein calculations were done here. At the time, we have gigaflop machines. You know, oh, that's fantastic. A gigaflop machine is a laptop. That one, not this one. That one, probably gigaflop. This in here, that was Cray ones, Cray YMPs are slower than my cell phone. So that's how things have changed. So where are we? This in here, 2013, there is a computer called the Milky Way. It's a Chinese computer. It's 54 petaflops. That's it costs $290 million. Yeah, that's they got money. Yeah, and that's the largest until March of this year. So Los Alamos has one that is called Trinity, and in Los Alamos Trinity doesn't mean what it means for religious people. Trinity, yeah. That was the nuclear test site, yeah. That's the machine. It is 70 petaflops, that machine. I was telling Ronaldo that the air conditioner room is bigger than this building. The computer is not that big, but the amount of heat that it generates is like a nuclear reactor. Heat. And I have no access to it. Carissa has access to it. Because they selected some projects before I arrived, and she got it. And that they can do 10 to the 11 atoms. They actually do galaxy collisions, all kind of really interesting physics. Navier Stokes to look at the turbulences. A lot of physics at a scale that couldn't be done before. It's done on this computer. So if this keeps growing up before the year 2040, when I'm going to be 84, I'm going to have a computer under my desk that is going to have 25 petaflops. That's the prediction. Then I can fold anything that has 10 amino acids, yeah, with time resolution, yeah. All right, so this is, many of you might be familiar with this. There's dedicated computers. 2011, the DE Shaw group published this paper where they folded 12 proteins in one paper. That's a science paper. And they did it by molecular dynamics. And they used this computer that is called an Anton computer. So this computer, the chip does the force field. The calculations of the chip is the energy function for molecular dynamics. So it's a specialized machine. It does the force field I showed you yesterday. You put polarizability, it doesn't do that one. You put bond couplings with angles with the length or whatever, it doesn't do that one. You want to use a 1012 rather than a 612 van der Waals, doesn't do that one. So essentially everything, a lot of the energy function is encoded in the chip. So a cycle of the computer is doing an energy calculation in a way. So it's super fast. I'll show you some calculations if I have time today for doing this. And notice, this is a homeodomain, it's a homologous protein to the protein A. They got it within 3.6 angstroms. They have a single is a small one, trip cage. It's a larger one. I'll show you some results, Billy. Interesting things. These are pure alpha, 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 beta. There is a beta WW domain here. So it's not just folding alpha helices. When we did protein A, that force field could only do alpha helices. If that force field I put protein G will make 5 alpha helices because it didn't have the right energetics to make beta sheets. So this was a big advance. This scared the heck out of everybody. That's why most people doing folding are looking at other problems because you cannot compete with that. Right? If it is in terms of atomistic simulations, if this is what you want to do, this is the competition. Great things, big service to the community. All these trajectories are available. So the nice part of simulations is not simulations. Simulations is the hard part. The nice part of the simulations is the analysis. So you can do all kind of fancy stuff. String models, Markov models. You have a theory on what kinetics, folding kinetics is. You get these trajectories, you can analyze these trajectories. Some of them, now they have done ubiquity, and they did milliseconds of ubiquity, which is 1,000 times longer than anything we will be willing to do. So these trajectories are available. Any of you students who wants to play, instead of spending 30 years doing a simulation, just download it. If you want to download it at the coarse grain level, in the sense that you get a frame every 250 nanoseconds or something like that, you can download it directly. If you want every, I think it's 50 picoseconds or so, the time frame. If you want that, you send a hard disk, they send you the trajectory back. I don't know if they do it in Brazil, but they do it in the US. So you can get these trajectories and do a lot of stuff. People are doing that. People are reanalyzing even what they did and publish in Science. People have reanalyzed it and done it and say, this model is not right, this is the better model, and so on. So this is a data bank of trajectories that if you can put your hands on them, do it and play with whatever idea you have to analyze trajectories. So what we can learn, here comes the pressure. Only 15 minutes for pressure. So what we can learn? Well, we can take systems that and put them under conditions that are not the typical conditions for the system. So these are high pressure, so for example. And it's interesting because people think, oh, there is a new field of high pressure. This is a paper published in 1914 by a person called Bridgman. Bridgman got the Nobel Prize in physics for studying matter at very high pressures, phase diagrams of water, all kind of metals, minerals, or whatever. He studied them. He got sick in 1940s. They told him there is no treatment, so he terminated his life. Says, okay, done, kill himself. So that's Bridgman. And I love this paper for the following reason. You see this in here? That's the paper. That's it. That's the whole paper. No BS of biologically relevant, of great significance, greater things since water with ice, none of that. So it's, this is the opening line. The purpose of this note is to state the fact of possible biological interest, not significance, which I have discovered incidentally, by accident, in the course of other work. And I'll tell you what the other work I think it was, the joke and the real one. If the white of an egg is subjected to hydrostatic pressure at room temperature, it becomes coagulated, presenting an appearance much like that of a hard egg. You can cook an egg in the cold without heating it. You just have to put a couple thousand atmospheres of pressure. And it's reversible. So you release the pressure and you have patience, it goes back to a protein, most of it. Well, some of it. So it is a reversible pressure effect. And here are the details. He put 5,000 atmospheres and so on. And here is another interesting line in that paper. The effect of temperature, which is not large, seemed seems to be such that the ease of coagulation increases at low temperature, contrary to what one might expect. So if you cool it, denatures more. That's cold denaturation. So cold denaturation was discovered in the 1950s by Privalov. You know, it was published in 1914 by this guy, just that sentence. And this is in Journal of Biological Physics. So what's the physics behind that? We can actually explain that. So here was the replicate change. We extended it such that we can actually do temperature and volumes. We can squish and compress and decompress the system in the same method with this replicate change. We can exchange between any states. In here, we have only done that twice because it costs too much. And then each one of these, you have to use either a processor or a set of processors. We have like 200 and some of these replicas, so that's why we didn't extend it to largest systems. But it works. And here is the physics behind it. How do you do the exchanges? It's very much the same as you will do the exchanges for the temperature replicate change, but now you have to put PV times beta in the partition function. So it's not a canonical ensemble. It's an isothermal isobaric ensemble where you actually put pressure and you want to change volumes at a fixed pressure for the system. And these are the rules on how to do it. The way you do it is that you scale your system to unitary measures. So essentially, all coordinates are scaled by L, and you change L. So you take your system, you divide everything by the length of the box, LXL, YLC, and then you scale it back by changing L, and that you increases or decrease the system proportionally. But the change in L is minute, right? Everything, everything. Yes, yes, yes. What do you mean clash? Yes, and if I change it by 1%. That's the difference between 1 atmosphere and 3,000 atmospheres. Yeah. It's 1%. So when you squish water 3,000 atmospheres, water is very incompressible. So it's nothing. Yeah, it's very little. Yeah, thank you, because that's exactly the kind of thinking that, things will jump on one of another. If you put terapascals, you're going to get some fusion. Yeah. I should try fusion in proteins. Yeah. So here is the GB1. This is a better hairpin that I showed you. This 250 replicas. Very short calculation. This was 2001, I believe. And here's the phase diagram. So here is density rather than pressure. They're synonymous. And here is temperature. Here is the contours that we actually get. So this is the system at lower pressure. As we increase pressure, the free energy. So here is very stable. Here is very unstable. So if you increase temperature, the system unfolds. If you increase pressure, the system unfolds partially also. And it's only folded in this very limited region over here. So this here is 8% density change. So it's very little change. This is 1,000 atmospheres, 2,000, 4,000, 6,000. This is the SPC model. We can actually study the folding and unfolding of that system. That's not the most interesting system. What is very huge numbers? Oh, yes. Yes, yes. Yes. So what we do is that we fix the target pressure and we let the volume fluctuate. in the replicate change calculations that we were doing. So the average, you get the right value, the fluctuations are huge. And that's the right property because it's a finite size effect, right? If you make the system bigger and bigger and bigger, you're going to get a much narrower distribution. But when you say huge, when I do a calculation and I fix the pressure to 1 atmosphere, that for us is 0, you get plus or minus 100 atmospheres, one way or another. But in here, we were looking at the steps of 1,000. Right, so there is a variation, but we're looking at steps that are way beyond that variation. So that's a fair point. Yeah, yeah. All right. So let me show you the diagram for this one because let me show you this diagram. This is the coolest diagram that I like. So Bridgman paper. This is tripcase, 20 amino acids. It's cooperative, folds and unfolds. It folds in 4 microseconds experimentally. It's a beautiful protein to do calculations because you can heat it with anything you want. You can put urea, you can put 5,000 atmospheres, TMAO, all kind of things, still folds and unfolds. You can do calculations at the 450 degrees Kelvin, you still have a fraction of the system that is folded. So it's so here are the free energies based on populations of folded versus unfolded, assumes a 2-state type model for folding and unfolding. This is the system at low pressure. It's actually low density because we're doing replicate change at constant volume in this case. So we're not using the pressure replicate change in this case. This is just temperature replicate change, and we do multiple runs at different volumes and therefore at different densities. So this is the low pressure. What is the pressure? Well, at about 300 degrees Kelvin is 0 or 1 atmosphere. Somewhere here at 500 degrees Kelvin it's 4,000 atmospheres. This one is about 1,500 atmospheres at 300 degrees Kelvin, and it's about 8,000 atmospheres at 550 degrees Kelvin. So it's huge rate. Not at, not at, no, not at constant volume. Yeah. Absolutely. This is what this is. No evaporation because I have a constant volume, and the critical value for water is 673 degrees Kelvin. The critical value of water. If you look at the phase diagram, there is the liquid vapor boundary, and it has a critical point at 600 degrees Kelvin. Yeah. So yeah. Now, in my water model, doesn't give a damn. Yeah, I can put pressure. Yeah, and I don't remember exactly at what pressure that critical isotherm is, but I can look at the phase diagram for water. So it's not a big concern. Yeah, yeah, yeah. Volume is fixed. So this change in pressure that you see here, these are essentially a replicate change. I believe this is 52 replicas. This is 52 replicas. These are separate runs, and these are the states that are sampled, temperature and pressure states that are sampled for the system. So this increase in pressure here is the ideal gas contribution to the pressure. It's PV equal NKT. And then there is a little bit that it comes from the configuration which is there everywhere, right? So that's where you see a difference between here and there. But let's go to the physics, and then we can argue everything about the simulations. That's cool. It doesn't give me a shade until I'm close. So, Bridgman experiment. So this is the phase diagram. This is delta U equal to 0 for trip cage. So let's do the Bridgman experiment. I fix the temperature. I pressurize the system, much higher than Bridgman did. And here, at about 8,000 atmospheres, I cross the delta G equal to 0 boundary. So the system unfolds at constant temperature. So this is the unfolding by pressure. Now, let me do the second experiment that he mentioned. I pressurize the system, and now I cool it. I move this way. I cross the boundary, cold denaturation. So you have pressure denaturation and cold denaturation. All it implies is that you have a diagram that has some curvature on it. So you have a cusp. In here, you have this diagram. So here comes the place where I'm going to challenge Diego, and he's going to have to put a barrier. He doesn't punch me. This system shows in this diagram in here. So you calculate the entropy. The entropy is the derivative of the free energy with the temperature, the negative of it. So here is the free energy. Here is temperature. Exactly here, the difference in entropy between the folded and unfolded states is 0. Right? Because it's a cusp, that's 0. And actually along this line is 0 everywhere. The difference between folded and unfolded. Below this line, the unfolded state has higher entropy than the folded state. Above this line, the unfolded state has lower entropy than the folded state. Oops. Right? You like it? Of course. Ah, great. Yeah. But people always think unfolded, high entropy, folded, low entropy. And the distinction here is I'm separating configurational entropy from entropy. So unfolded has higher configurational entropy, but the solvent also has a difference in entropy. So the solvent above this line is more ordered than the solvent below this line. And that difference compensates the configuration, what you will call the configurational entropy. And along this line, it compensated perfectly well. And notice this line in here is the line where the volume changes are 0. So typically, the driving force for pressure denaturation of proteins is that in the folded state, you have cavities inside the folded protein, and those cavities don't necessarily are filled with solvent, with water, so they occupy volume. You also have hydration shell that also contributes to the volume difference between folded and unfolded. Now you unfold the system. When you unfold the system, you have different set of cavities, smaller, principal, and then when you put pressure, Le Chatelier principle says you go to the low volume state. So as soon as you pressurize, the system should reduce the volume. And the way to reduce the volume is to unfold, expose hydrophobic groups where they're more compressible, the hydration shell, and then disappears most of the cavities. So this is what drives pressure denaturation. And how much is the driving force for that unfolding is P delta V. And the delta V is milliliters per mole. If you take staph nuclease, which is 140 some amino acids, more or less, 150, volume change is about 100 milliliters per mole. That's about 3 water molecules, the volume of 3 water molecules. It's nothing, right? So the volume changes are, but when you put P delta V, so you have few milliliters per mole and you have 5,000 atmospheres, they give you 1 or 2 kcals. That's all you need to unfold the system. So this is we can go into the details, but we have 39 seconds, so this might be a good place. I caught something here. The bat. So the next lecture I'll do the bad and the ugly, if that's okay. The bad is this guy, and the ugly is a membrane protein. So thank you. Questions? Ronaldo? Uh-huh. What do you mean can handle it? It can handle it. That is, describe reality is a different thing. Yeah. We tend to believe that, but if you look at the models, they never explore pressure. Yeah. Now, when I say, for example, the diagram that I had that it shows the ellipsoid at 8,000 atmospheres, we actually published a paper this year with collaborators doing NMR on trip cache, looking at the conformational changes, and they didn't put 8,000 atmospheres. They needed 2,500. They didn't. So the scales are all off. The scales are off also on temperature. Notice that it depends on the force field. Actually, with the 99 SB force field, the melting temperature, we get it within a few degrees Kelvin for trip cache, but it's pure luck. I mean, we don't expect that kind of accuracy. So everything should be scaled in some way. Now, where the differences come from, for the water model, right, I mentioned yesterday, we have interactions that looks like this. This is Van der Waals. This is 1 over R to the 12. This is fictitious. Right? This R to the 12 is not real. When you're simulating a system's particular water, you're not sitting here. You're sitting here. And the pressure, if you look at how you calculate the pressure from a canonical ensemble, is very much the derivative of the potential with R, ensemble average of it. So you're looking at the derivative here, tells you what the pressure is. So if the pressure is this, that fixes it. If the pressure is what people call it should be a whale shape, this slope could be higher or lower, I don't know. So this derivative is going to be something else if you actually model it appropriately. So there is a model long time ago from the 70s from Enrico Clementi that he parameterized everything with quantum mechanical calculations. And this part in here is e to the minus 1 to the 12, I believe. And that's a slightly different, I mean, some coefficients here and there, right? That's and this is quite different from that in terms of the parameterization. So the actual ensemble average of the pressure is something else, which is not what is in here. So when I make the diagram, I put something like that, and I put here, right, 8,000 atmospheres, 800 megapascal. In reality, that's bad, right? I wish I had here P over PC, if I only knew what that was. That way I will scale, say whatever the appropriate pressure for these systems are, they're all scaled. But I don't know what this is for, even for these water models. I don't know if that exists. And the same here, right? We do that trick for minimalist model. We divide by T folding. And then the folding temperature is always 1. You always get it right. That's just eliminate one parameter. So yeah, the value of pressure, the phenomena is there. We pressurized. When we pressurized, hydrophobic effect changes. I skip that overhead because I saw look at the watch. When, for example, if you have a bunch of hard spheres, I'll go there because I think it's relevant, at least for the discussion and for a sense of what is pressure doing for the different interactions. So imagine you have an ion in water. You have a very rigid solvation shell around that ion because of electrostriction. That's what the chemists call it. You pressurize that ion. The hydration shell is already high density, so you're not going to compress it much more. So that ion, when you put pressure, ion-ion interactions very much stays the same. You're not going to change that. Hydrogen bond, again, either hydration or hydrogen bonding is polar-polar interactions, and those interactions, when you pressurize the system, the density is already compressed. The system is already compressed. So by pressurizing, you're not going to break, because that's going to reduce the volume. It could reduce it because both groups could be solvated, and that could enhance the density among the two groups. But in general, that's the competition that you have to look for. Now comes hydrophobic effects, non-polar atoms. So non-polar atoms, these are calculations we did. This was a summer student. Just make a cluster of methane in water, completely unligated. And you do a simulation, it makes a cluster. Cluster oscillates, and it's very much a blob. It's a blob because it costs energy for these particles to come away from the blob, because they expose non-polar area, and then water around those groups is frustrated on how to solvate that group. So it prefers to form these clusters. Now I pressurize, and these clusters come apart. So the hydrophobic effect is weakened with pressure. So when you have a protein that part of the folding is driven by hydrophobic interactions, it's going to open up and expose these hydrophobic groups. And why is hydrophobic effect weakened? When you have a group like this that is solvated, there is a reasonably well-accepted model that the hydration shell of that group is a caltrate. So you have a sphere, and the waters are mostly optimizing on how to make the most hydrogen bondings around this object that just got in the way. And for the water, that's a hard sphere because it has absolutely no charge, nothing. It has a little bit of van der Waals, but you can actually model this with hard sphere, so it has absolutely no interaction with the water. So I have this ball, and water is going to be arranging around it, and the density of water here is lower than the density of water around water. When I pressurize, I can bring this water inside and still solvate this hydrophobic group. While in water, when I pressurize, the hydrogen bond network is such that I pressurize, I cannot reduce the volume. I reduce the volume, you see, 4,000 atmospheres, 2%, just very little. Compressibility of water, those of you who have worked with cars, you have your nice car, you drive it into the river, and water gets into the pistons, you blow your engine. Because when the piston tries to compress water, it prefers to crack the motor, the metal, than to compress water. It doesn't compress water, cannot compress water. That's why it's called hydrostatic pressure, because water is the medium to transmit pressure. So that's the difference between configurations like this versus configurations where it is cluster, is that all the water nearby here can be compressed. So I gain volume, I lose volume by compressing, and putting pressure means I want to lose volume. So I drive toward this kind of configurations. Don't ask me why so many twos and not more, because we didn't explore that. I mean, pair and triple correlation functions should have told us, but we didn't look at that. All right. More questions? I'm here the whole day, and actually the whole week, so I like to be challenged, and if I get really pissed off, we drink. Thanks.